Okay, now we are starting the next presentation that will be given by Ilya Kosmodemiansky from PostgreSQL Consulting. You're welcome.
Alexander. Hi everyone. I work in for company PostgreSQL Consulting, and today we'll spend around 40 minutes talking about databases and Linux internals. Thank you for coming to spend your weekend on such funny stuff. So first of all, why this exactly talk? Linux is a most common operating system for databases. That happened historically, but now it's the fact. Most of the databases performs better on Linux, and there are plenty of reasons for that. Many DBAs run into some I/O performance problems, and this is probably one of the common issues with high workloads. I used to give lots of talks on Linux tuning for Postgres, for sometimes another databases, and most of all it was like checklist approach. So I just explain there is this and that system.ktl kernel parameter and some mount options and so on. And if you turn these and that, probably your database will be okay. But that's true to up to certain workload. Then you run into something specific that can be difficult, and you probably want to learn something more about how it works internally to make a decision by yourself. So that's why I decided to explain things in some details in spite of this checklist approach. So today we will talk about how it works internally. Of course, that will be some kind of simplification because, you know, it's a complex topic and it's basically the normal topic for a thick book if someone dare to write that. But not for a single talk. But anyway, I try to explain some things, and I hope it will be good. So the main I/O problem for databases is how to maximize throughput between disks and memory. And this is kind of a tricky thing because normally we assume by I/O that I/O it's about disks, but for database I/O it's a complex problem, and CPU can be involved, database workload can be involved, and one and any part of operating system, Linux in our case, I/O stack too. So we will talk about many things related to memory management in Linux, related to I/O stack in Linux, and maybe less we will talk about database specific things. For that purpose, normally we make some checklist style talks to just remind that, okay, this and that settings helps in this and that way. A typical database, why it's a typical? Because most of the modern databases work in something like that. Oracle do that, MySQL do that, Postgres do that. The details can be different, DB2 actually too, at least one for Linux, Unix, Windows. Things can be different in details, but in generally the idea is the same. Database has some sort of shared memory segment if it works like Postgres does with many Linux processes which interacts between each other using shared memory. And it's a huge piece of memory allocated for so-called page cache. Page cache, it's basically the database pages which are read to that cache, and if you change something, the whole page will be marked as dirty one. And another task is to synchronize that correctly back to the disk, because if you change something in shared memory, that will be inconsistent in relation to the data file. So for that purpose, most of the databases have some mechanism called write head log, which is used to put the restore, mostly redo information to the disk, and we write that sequentially. That is slightly easier in terms of I/O problems too. And after that, special dedicated process like checkpoint comes and synchronize dirty pages from shared memory to the data files. That can be made in different ways, and most of all, not only checkpoint do that. In Postgres we call that background writer. In Oracle there is a DB writer which performs some extra synchronization, but those kind of details is not so important for us now. It's for database specific things. The most important thing we need to stop at is that, for example, Postgres used a buffered cache. So Postgres write and read data twice. So we let operating system to put the data we need to page cache of the kernel, file system cache, kernel buffer, page cache. There are lots of confusions between those terms, but basically we, in this talk, will assume the same under all those terms. And then we write pages, then we synchronize that back to a disk. We usually knew how to run that from Postgres to the kernel, and when we call fsync to synchronize everything through to the disks. And MySQL, for example, can do that in more progressive way using ODirect to bypass page cache and to do that slightly faster. So take in mind, I'm talking that something MySQL can do better than Postgres. But that's more complex problem. We need to discuss it probably in more details. Oracle do that in a different way. It uses ODirect for I/O, but normally it has its own scheduler inside, and it can manage how to put pages more efficiently, and it uses ODirect together with async I/O. So that's another topic, and Oracle do that even better. So what details about these structures and how they work we need to understand better database performance on Linux. Key things about such workload. Shared memory can be very large. So basically on the modern server it can easily be half a terabyte. Keeping these page synchronization is a difficult task. When checkpoint came, it can be a lot of I/O, and that can be really heavy. When we write a head log, it should be safe, fast, and reliable. And practically one and every layer of this typical database schema involved in this process. So first step, how normal Unix allocates memory nowadays. We are talking about Linux presumably. Then our Postgres asks for a page. It asks CPU to work with page to allocate that. For that purpose, Linux has so-called memory management unit. And here it can be done in many ways. The most easy thing is if this operation of translation from virtual addressing methods, which is common for user space, for applications, for CPU, is cached in so-called translation look-aside buffer. This is a cache for those kind of instructions. Of course, it is simplified here because normally we, on our modern server architectures like Intel's and so on, have multi-tier caching also in translation look-aside buffer, as well as in L1, L2, and L3. If it is in TLB, it saves us a small amount of hops, and then we go through our caches and get our page, and it's allocated and mapped. And that's a good case. The bad case, if we have so-called page fault, and we need to make MemoU to allocate our page from physical memory, and MemoU in that case allocates page, maps it, and put the information about this operation inside translation look-aside buffer. That's the round trip of the pages. How that can influence a database. If we have a huge piece of memory on our server, and operating system will allocate that traditionally in small 4 kilobyte chunks, that can be really painful because the size of this cache increases itself dramatically. And as probably you know, as with one and every huge cache, that can cause the cache misses and lots of problems with overhead for translation look-aside buffer inside memory, and that's bad. So for that purpose, we usually recommend for DBAs to use huge pages. The idea is quite clear. We have huge chunks that reduces overhead until B reduces probability of page faults, and that works quite better. But small notice on transparent huge pages, which normally assumed as a more progressive technology, because you not try to allocate all the pages at once statically, but you can do that in more convenient way to special daemon runs through the memory and analyze if some small pages should be grouped into larger pages. Theoretically, that works well, but for databases, because they used to use huge amounts of conscious shared memory, that can be very bad, because if that piece of shared memory runs into defragmentation, that can issue serious problems. And those kind of issues are known for Oracle, MySQL, as well as Postgres. So basically, you want normal huge pages in that case. More complex thing and more influencing on databases performance is freeing memory. Basically, in Linux, there are several methods how it can free memory if the memory is needed. First is putting it to SWEB, and that's not a common Unix old school meaning of SWEB. In old Unixes, SWEB is to put the whole process to the SWEB. In Linux, it's most likely some kind of anonymous paging, to be precise in terminology. So basically, some pages which are used by certain process can be put it to SWEB file or to SWEB device. And there is a parameter swapiness which can control the preference. So it can be 0, which totally disables this mechanism, or it can be 100, which says to kernel that kernel should prefer to page out pages, should prefer to put pages to SWEB instead of page out. Another mechanism is so-called Pageout, and previously it was PD flush, KD flush, now it's so-called flush threads, because currently Linux has lots of free lists, generally one free list per NUMA node and sometimes per device, and this daemon works like that. If we have some pages which we can return back to free list, a list of pages which are available to allocate. It puts to the end of this list those pages. How it works, it will be 2 slides later, but the idea is that can be not actually freed page, but page available for new allocation. It can be some information inside. And for that purpose, there is another mechanism, so-called reclaim. So if this page will be required back into page cache, a Pageout daemon can take it and put it back. The free list normally use its head to allocate and to free memory. So the normal functionality is that if we need lots of memory, free list shrinks from the both sides. And at some point it can meet VM min 3 kilobytes limit. And if it happens, there are several options what to do. One option is to do more intensive page outing, not the background one, instead of background one. And if it's possible, it grows slightly and everything is okay. But if not, there is a kind of emergency mechanism which is known as OneKiller, out of memory killer, which comes and forces some pages to be put it back to the free list, and generally the mechanism is to kill some process. If you run a database and you try to kill the process based on some score which is actually connected to how many memory consumes the process, you can guess what kind of process will be killed. So this is some kind of real emergency thing. All those mechanism has a common name, ripping. That means how to free those things. So some another kind of comments on these mechanisms. Pageout happens if someone calls fsync. For example, if you run Postgres and it's called fsync, every time you will free memory like that. There is some limit. By default, it's 300, which means 30 seconds, and you can change that if you want. And if too many dirty pages accumulated in page cache, which are described by this parameter, dirty background ratio and VM dirty ratio, as well as mutual exclusion parameters, dirty background bytes and dirty bytes. That's by default, it's 10 and 20% of total RAM on machine. And in that case, the Pageout actually happens too. We used to recommend many settings for database for that parameters if you are running your database on rotating disks or on rotating disks using RAID controller with cache and battery. For modern SSDs, I mean server-side SSDs like Intel 3700P, PCI Express SSDs, this parameter is not so necessary because the performance of such SSDs normally is much better than rotating disks, and it's not necessary to change those parameters. Another takeaways are that normally there is one another parameter which regulates how many memory can be allocated as a virtual memory. So basically we call that overcommit, and if it is 0, it tries to allocate memory like SWEB plus available RAM and tries to minimize using of SWEB. That's not very good for database because on huge machine with a lot of memory, most likely some piece of memory will be still free and SWEB will be used. For database, using SWEB will be terribly slow. That's not thing you want. And 2 is do not overcommit at all. So in that case, system uses entire SWEB plus 50% of available memory. You can change that to another percentage. And that's more recommended thing for database, of course, if you provide a room for your processes like total memory plus some sort of SWEB, just to be safe that OneKiller will not come and kill everything. Another parameter which involved in these things, I already mentioned it, should be reasonably high, because if you have enough memory, it's not a good idea to be afraid of OMKiller hit this parameter if you have proper mechanisms of flushing well-tuned from side of database and from side of operating system. But for many things like intensive network connection, intensive SQLnet, transfer from database and back to database, you need a lot of memory available for those connections. For example, if with Postgres you're using PG bouncer, it should allocate lots of pages to work with non-blocking sockets. So basically you can increase that to some rational size based on how many memory you have available on your server. And VM swappiness is more important parameter which controls this preference to swap or to Pageout more directly. On older Linux kernels, we used to recommend to switch it totally, literally to put 0 here. But on modern kernels, which we recommend to use for databases now, it's a bad idea because it's totally swap off, and then OMKiller comes. It probably will kill your database. That's not the thing you want, because it can be disastrous and you can probably will not recover from that, or at least you will need to recover from backup, which is a bad idea. By default, it's 60, which looks like not a reasonable value. So we recommend to decrease it to 1, which means operating system still can use swap just as an emergency measure if we run out of memory, but not kill the process. And probably if you have a proper monitoring, you will see that if swap is used, you need to check the state of your memory, how many memory allocated in that manner and in that manner using procfs, and to figure out what to do with that. Your database would not like OMKiller because, you know, it will be bad. OMKiller settings, it has separate settings. It's really a bad choice to use them because the settings has a very obvious name. So you can disable OMKiller, then you put 1 to these settings. So if you have 0, that means OMKiller enabled. If you put 1, it means it disabled. But in that case, instead of OMKiller, kernel panic will come. And I don't think that it's a better idea than OMKiller, but because basically you will have the same problem. And yeah, that's bad. Another piece of things involved in I/O is obviously file system. And the most important thing when you run database, which you probably run on a good disk with cache, and this cache is protected. If it is SSD cache, on disk cache, it can be protected with a capacitor which has enough power to put the data in case of emergency to the non-volatile storage. Or if you have RAID controller, which probably has its cache, and you have battery, you need to disable the so-called write barrier. This mechanism is developed mostly for desktops, laptops, and so kind workaround workloads. And the idea is then you have a huge page cache, huge kernel buffer, and you have all your data entries, but the journal entry is somewhere on top of this, and it takes long time to put it to the journal. That's some emergency for operating system, because if the power goes down, it can never repair that from the journal data, because by the outage, this data will be losing. So operating system kernel scheduler tries to resort the kernel buffer. It issues special system call, GBD barrier. And this system call means that we stop all I/O up until we found the journal entry and put it in place. From time to time, it tries to check that, and if it is the case, it stops I/O and trying to resort the kernel buffer. And if we, for example, we're using Postgres with half terabyte of memory on server, most likely it will be like 128 gigabytes of page cache. That will be really, really slow, and you better disable this write barrier. But just take in mind that you can only do that if you have some autonomous protection things like capacitor or battery. And of course, that all works for ext4 or XFS, because things like Btrfs, like ZFS, they're quite convenient in many ways to use with databases like transparent provisioning, resizing of partitions, and so on. But you know, that's not about performance. They have lots of another bottlenecks. IO stack together with database looks like that. It's pretty simplified one, but you know, you have some shared segment in the user space. In case of Postgres, it's shared buffers. In case of Oracle, it's the page cache and system global area, and MySQL has that inside in a DB. Then you need to make your dirty pages travel fast. And another thing we already talked about, ext4 for example, is the piece under block device interface. In block layer we have so-called IO scheduler, or to not get confused with CPU scheduler, we call it elevator. And that from time to time can help to work better with IO. Elevators can be different in their approach how to help pages get to the disk faster. Previously in Linux there are less of them. Today we have this diversity of schedulers, and for modern PCI Express SSDs, for fast SSDs, for disk arrays of enterprise grade, the good recommendation can be NOOP or none. We do not call that normally NOOP, we call that no op, no operations. So basically from this name it's obvious how it works. It works like it do not do any kind of resorting, it just maximize throughput through the scheduler queue and put that to disk. And in that case, we think that, okay, the I/O performance of our hardware layer is much more faster to accommodate all these I/O without any kind of overwhelming. So deadline can be good for rotating disk because it uses slightly more complicated queuing, like separate queue for reads, writes, and for instructions and so on. But to be honest, rotating disk on high performance database which can run into such things like I/O problems, it's some sort of the obsolete things, because nowadays SSDs for databases are not so expensive like it was even 2 to 3 years ago, and lifespan of SSDs is quite impressive now and quite comparable to the best mechanical rotating disks. So I don't think that deadline is a good option now, because if you struggle with I/O problems, most likely it's much more easy to afford proper SSDs for that purpose. CFQ is more universal, and today it's a default one. Basically, it has some ideas how to make I/O faster using some groups and processes, and you can ionize that. Maybe it's a good default option if you do not know what benefits of those two can be, because it allows you still to utilize SSDs properly, it allows you to work on the bad disk properly, and most important, if you want, for example, ionize your backup process, or sometimes we do that with Postgres, for example, we ionize auto vacuum process and so on and so on. This is the only scheduler which allows you to do that, because ionized works only on top of this scheduler and without any extra layers like LVM and so on. So thanks to my colleagues Alexei Lisovsky and Maxim Baguk, who made lots of research on that topic and give me an opportunity to share that with you. And if you want, already the slides should be on SlideShare. I hope the automatical service of uploading works well, so they are there, I think. And before the questions, I would say that I have some PostgreSQL community giveaways like laptop stickers. Come and grab that after the talk. And I have some 20 years Postgres paper magazine, which can be easily transferred to 20 years Postgres thing you can put inside your office. So basically questions.
Thank you very much for this well-structured presentation.
Thank you.
And now we have about 20 minutes for questions. Okay,
Hello, thank you for your talk. Can you please say about score adjustment for OM inside the PROC-FS? You missed this. it was on your slide, but you didn't say about this. Why you use don't overcommit, but not score adjustment?
Yeah, should be score adjustment here.
Yeah.
And the name of this slide actually says something about why I do not consider that as an option. So basically, that's obvious why you should not do that. For this one, it's usually can be a pain because if you use this mechanism, you have basically two options. First option is to forget to change these after you restart a database, for example. And I saw that many times. So people do forget to do that and rarely do that automatically. So you have wrong PID and basically will not work. But that probably can be an overzone thing. But another thing is that you have probably a dedicated database server. And the single thing which can probably cause out of memory wear is a database. So if you disable OneKiller, particularly for your database, most likely it will be not killed, and that will lead to kernel panic. So basically, I don't think that is a good option. The only thing you can benefit probably if you have some workers which working with rebuilding indexes in case of Postgres, for example, and they need lots of process memory. Probably you can do that for them, but you know it's really a corner case.
Oh, okay. It's for dedicated database server. It doesn't work for dedicated database server, but if you have something, for example, Redis on the server with your database.
I personally will be happy to keep OneKiller enabled for Redis, but I got your point.
Another questions? Yeah.
So you described the I/O schedulers in general, What about your personal experience?
I would say that some people in our company as well have some ideas that for certain workloads we need to figure out which one is better. For example, NUP and AN for SSDs. From my experience on modern kernels, CFQ is a good default. So basically, you really can win only a small percentage on that things. So CFQ is probably the best one.
Thank you. Next question.
Thank you. Could you describe more details about I/O approaches difference between PostgreSQL, Oracle, and MySQL?
That's a good question and probably the topic for a huge talk. I was lucky enough to leave some room for that. But briefly, the idea is that PostgreSQL as well as MySQL work on top of operating system and rely heavily on the operating system mechanisms. Oracle always pretend to be an operating system itself. So it basically has its internal scheduling mechanisms and so on and so on. And the best performance you can achieve on Oracle, you probably can achieve using automated storage management, which basically bypass all the operating system mechanism of I/O. And it is asynchronous, multi-threaded, non-blocking, and so on and so on. Postgres, as I said, puts the data to the kernel and runs fsync to be sure that data is inside the kernel. Because mostly I would say because of support only small amounts of operating systems, MySQL can implement all direct now with InnoDB. In Postgres, there are ideas how to implement that, but work is in progress because if you do that in straightforward way, probably your Postgres will not be run because of data alignment and that the mechanism which are reading data inside Postgres buffer cache, shared buffers, are not designed to using direct because they are designed to take the already the prepared pages from the page cache without any alignment problems and so on. Yeah, there are many problems with that, but the general differences between Oracle and those two, because Oracle uses different approach to I/O. Yeah.
Thank you. The first one there.
What tools do you use to measure latency at Postgres level, VFS layer, and block layer?
Oh, there are a lot of tools actually. Basically, you need to use a basic monitoring and have at least IOStat information on that graphs. But actually, in Postgres, we have things which you can correlate on these graphs with disk utilization from IOStat, for example. And we'll see that, for example, Postgres performs checkpoints at using the information from Pageout BGWriter technical view. And you'll see that this I/O utilization spike, for example, is caused definitely by checkpoint because you have lots of buffers written by checkpointer and so on. So you'll see that. Nowadays in Postgres there are some attempts to implement some things like Oracle wait monitoring, but it's really work in progress, so it's not production ready. And basically then we try to figure out which part of latency was on Postgres side and which part of latency was on operating system side. We use some kind of perf scripts like perf-top and so on. So, and then manually trying to figure out which part was caused by what problem.
Okay, thank you.
Thank you. Okay.
Hello, thank you for report. Can you switch to slide with the SWEBiness parameter?
This one
Yes,
or the schema?
No, with VM SWEBiness. Yeah,
Yeah.
SWEBiness 0 is not disable SWEB. It's just say do not allocate in SWEB before all of RAM memory is used. If you call allocate, you didn't call OneKiller. You just go to swap.
Normally, yes. Then you try to allocate memory. There is an option to call OneKiller or not if no swap available. But according to our experience, starting from 3.2 or something like that, not the first kernel version 3, the behavior slightly changed. And if you try to set swap to 0, most likely before using swap, OneKiller comes first. It will be not disabled by allocate. So then allocate try to allocate memory. It will call for OneKiller first. This behavior, like you described, that was typical in slightly older kernels, like 2.6 it was typical.
No, it's in our production and we didn't use.
Maybe you did not run into that, but yeah, we did. Yeah, and many customers actually.
Okay, thanks.
Thank you. I remember that it was a question from him.
Question about Socotra amplification. Could you say if one column in one row modified, say, integer of 2 bytes, how much data has to be written down to the disks?
Actually, the idea is that database modifies the data inside shared memory, and then it puts that to the disk in really huge amounts. So there is no such case there because, for example, Postgres has 2 settings how to call checkpoint by maximum wall size, and on huge workload it can be normally more than 10 gigabytes. So
Define one column. When one column modified in one row.
Actually, nothing happens. Basically, we write only the wall buffer, and the wall buffer we flush entirely. So we'll lose some I/O effectiveness at that point, like Oracle administrators do. Then they set read the buffer to huge size and do not have such amount of writes. But I would say nothing happens because the only checkpoints will occur in 1 hour, and that means you basically have no huge I/O workload, or it will happen if you have huge write workload, then you accumulate enough wall. And in that case, it will be gigabytes of dirty pages from shared memory. So I do not see the case how to optimize such a thing.
Okay, thank you.
Thank you. Еще вопросы, господа? На русском языке тоже можно. Okay, any more questions? Looks like no. So actually, before we will leave for well-deserved lunch, I would ask you to pay attention to this page in the notebooks. This is about the report evaluation. So please put your marks. One the worst, the SHE-5 is the best, and we will collect this at the end of today to understand your interest. And let's say once more, thank you for Ilya for his presentation.
Thank you, Alexander.
Thank you.
And thanks you all for coming. I appreciate any kinds of feedback.